So if we go to courses, R class 236, files, lectures, review slides. This slide, review SNE, is going to become important, particularly if you did not have me. That would be Lydia and Duke for first semester. Within this slideshow, I thought it was my condensed version, but apparently I posted the wrong one. This is the long one. But this shows, when you're looking at substitution elimination reactions, how you would decide which mechanism to go by and kind of the complications within it. So the big thing to get or remember out of this whole presentation was actually something that our textbook gave that I then modified, was this table. You should be looking at the strength of the nucleophile, strength of the base, substrate, solvent, and then heat. Leaving group is super, super tiny font because, well, for the most part, all of them need a leaving. Well, it's not even for the most part. They all need a leaving group, and it has to be good. If you don't have a good leaving group, the reaction doesn't happen. Right? So if you go through and kind of rank based off of what is necessary. So if you have a strong nucleophile, that favors SN2. So we could go through and put a check mark in the SN2 box. Right? But if you have a strong nucleophile, more than likely that's also a strong base, so you could put a check in the E2 box. You can then go through and look at the substrate. Well, the substrate is primary. A primary substrate favors SN2. So if that was all the information we'd have, we have 0 checks in the SN1, we have 2 in the SN2, 0 in the E1, and 1 in the E2. That suggests the mechanism we should be looking at or trying to use to predict our product would be the SN2 mechanism. Right? So whenever you're trying to decide between those 4 mechanisms, you have to know those component parts. Right? You have to. The explanations on those component parts are kind of what's going through the rest of this. And then there's some review stuff from 152, don't stress, don't stress, don't stress. Mechanism, kind of important words to tie. So this is all useful information, and it gets at details, but it's more than I actually wanted because I wanted just the summary. So I apologize for scrolling because it may make you dizzy. Just close your eyes. Count to 10. It's making me dizzy. Oh, there it is. Okay, now you can open your eyes. For a substrate, what we're concerned about is steric hindrance for the SN2, so I want the least sterically hindered substrate, the most stable carbocation. Okay, so this goes through and lists out what we would expect for SN2 and SN1. Notice it also addresses issues like stereochemistry and sometimes rates. Okay? Rates was very, very important for the first semester exam, less important for the second. A little bit more scrolling to get to our summary. Our summary for the E2, again, looking at those important patterns. You should know these. Okay? If you don't, you need to be reviewing this content. Because you will see questions that get at these individual aspects. Right? These are things that we've discussed this semester because we've seen SN1, SN2, E1, and E2 mechanisms throughout this semester. We just didn't look explicitly at the rules as we did in first semester. Okay? So I still highly encourage you to go back and review those. It is important. You should do it. There's the table again. And then kind of some questions that you could ask yourself to go through and do solves. Okay? So please take advantage of, is that the close button? Yep. Of using that slideshow to help you kind of get through it. Okay? After that, the rest of the plan for today is what was already starting to be alluded to. Buttons. No, because that's that. Oh, I know what I was going to do. Yeah, we're going to be pausing and playing every so often. Your first pass in that 10 minutes was reading all the questions and being like, this is some bits and pieces of information that I think I can put down so that I can answer this question later. Okay? Because if it gets to the end where you just have to guess, you aren't reading the question, you're literally just writing a random letter down. Okay? So I like that you're going back, well, I want to read the question to figure out what I should guess. That's good. Get that information down first. Then start worrying about answering the questions in detail. Okay? So spend the time to make sure you've at least seen everything. Okay? I did notice a lot of people going through in sequence. Nothing about this says question 1 is easier than question 7. Skip. Read them all, decide which one's the easiest, start there. Okay? So that said, I will attempt to go through and look at these and see how badly I can screw this up. So question 1, which base was used quantitatively? Jiminy Christmas. Convert this dimethylamide into an enolate. So things that I would identify: base, negative, quantitative, complete. 2 hydrogen atoms in this compound undergo deuterium exchange. Deuterium is D, which is equal to hydrogen exchange, so I'm talking about a proton transfer. This is acid-base. And actually, I know acid-base reactions. 2 for sure is an answer. 3 is acidic. The other ones I don't see as acidic. Which compound is a product of an aldol condensation? Aldol is an aldehyde and an alcohol. But then it says condensation. Condensation is an elimination, which means I'm getting an alkene. Okay. In doing an elimination, I need to get rid of a leaving group. The best leaving group here is going to be the alcohol. So I'm looking for an answer that has an aldehyde and an alkene. 4, which set of reagents would accomplish this conversion? Yeah, screw off. 5, yeah, quite literally, I'll just move on. 5, which compound forms the greatest equilibrium concentration of the enol tautomer? Yeah, I'd probably skip that. An aldol reaction can produce an addition product or the dehydrated addition product, condensation product. What factor favors the formation of the dehydration? Okay, so we're saying why this? Which is not true. This one would probably be the last question I would ever answer. And now that I've read everything, I'd go back through. Okay, that acid-base one, I know my acids and bases. I said 2 and 3 were acidic. Answer is A. 5, I said I needed an alkene and an aldehyde. There's an aldehyde, there's an alkene. That has the alcohol, that doesn't make sense. That has an alcohol, that doesn't make sense. This is an aldehyde, but it has a carbonyl. Oh, that's right. Just because it's an aldol doesn't mean it's only aldehydes. We did those with ketones too. Okay? So this has a carbonyl and the alkene. But the reason I would call it an aldol is because they're close to each other. Otherwise, I would just call it an aldehyde and an alcohol. So I'm looking for the one that's going to put these 2 species as close as possible to each other. There's A. After that first one was acid-base because we had a base. So I'm looking for a negatively charged species. I want complete conversion. Complete conversion means I need the absolute strongest base possible. So which of those is the strongest base? They all have a metal, which means they all have negative charge. I swear that says lithium right there. I think that says lithium too. And I have a nitrogen with a negative charge. So I'm looking at oxygens with a negative or nitrogen with a negative. Of those, the strongest base. The base needs to be able to share electrons. Oxygen being more electronegative than nitrogen, less willing to share its electrons. C. After that, I've got a Y and one that I'm saying I don't want to do at all. Can produce an addition product, dehydration. What factor favors the formation of the dehydration? So to do that dehydration, I'm losing that hydrogen and that OH. Excess aldehyde, I don't see how that favors the removal of the H or the OH. Excess base. Base could help out. Base could remove that, so that's possible. No alpha hydrogens. Yeah, that's not good. That's actually really bad. Stabilization by conjugation. Okay, conjugation, we're saying this pi bond is conjugated with that pi bond. Yeah. That would actually reduce the energy of my carbonyl pi bond, lowering the energy of my product. I actually like that answer a lot. Stabilization by conjugation. Okay, 5. Which compound forms the greatest equilibrium of the Enol Tautomer? This means I have to know what the Enol is. Okay. For that to happen, oops, not an equilibrium. I have to be able to remove that hydrogen. That hydrogen needs to be acidic to get across. So which of those has an acidic alpha hydrogen? D is wrong. C at least has a hydrogen. A has that hydrogen. B has that hydrogen. A has a double resonance. That makes A even more acidic. So that's going to be my best bet. Would accomplish the conversion shown. Oh, this is going to be awful because I can barely see it on my screen. The difference between those two is just the CH2, CH3 versus a hydrogen here. Okay. That hydrogen I know to be acidic because of resonance. So I want to do a base, giving me a negative carbon, which means the methyl or the ethyl carbons that need to come in have to be positive. I need to have a positive CH2, CH3. I'm going to guess only one answer matches that. Oh, I got them up there. So I said base and a positive CH2. So answer A gives me an OH. That would give me a positive CH2, but OH is a bad leaving group, so A doesn't work. B gives me the base followed by positive, so B works. C gives me a negative because of the alkene. D gives me an acid, and I said I wanted a base. So B is the only one that makes sense. And then my favorite of favorite, true-false questions. Not true of the aldol. I would remember back to what I said for the aldol. Complementations, formation of a new carbon-carbon bond. Interestingly enough, my notation didn't have that, but that is true. We're linking two carbon structures. The key step in the mechanism is the attack of the alpha carbon of an enolate ion on a carbonyl carbon. That's pretty darn important. Key could be a bit of a weird piece of information there, but that is going to be important. Dehydration of the aldol product is often observed. Okay, that should immediately be a tip-off with that word often. Okay, we're saying not true. Often is a qualifier saying one way or the other. That's going to be hard to completely eliminate that answer outright anyway because it says often. That could be true or false. So that's a bad idea. The enolate is favored at equilibrium. Whoa, no it's not, because that would be a negative carbon. Okay, so D is absolutely not true. There's my answers. And that was about 7 minutes, looks like. About a minute per question, shuffling over each and every single one of those. The other thing that I want to add here, look at everything that is written down. Okay? I, in theory, know these answers. I could do all of that work in my head. I'm not. Okay? so I want the answer right. Okay? Which I guess we could step back from and check. Actually do it. That's always fun. Maybe I should stop recording right now. So what do we get? We said 1C. 2A, yeah, that's nice. 3A, yeah, so far so good. 4, I only announced that out. Would I say B? Yeah. 5A, 6D, 7D. 100% not failing yet. Okay? So, I want you to see how I think through this. All of those thoughts are things that you should be going through and doing. Okay. Questions about anything that's written up there, why I wrote something or why I didn't write something? Okay. Was there anything I wrote up there that you were like, whoa, where'd you pull that from? Or all of that, you're like, yeah, I knew that. And I did do that fast. So if you're like, whoa, how could you possibly do that? Yeah, I did it fast because I want you to be able to see kind of the level you should be going at. So if we take a look at 6, actually, can I clear everything? Yeah, of course I don't have that picture in there. Well, that was fun. So don't clear everything for the future. Let's take a look at 6. Okay, so aldol reaction can produce an addition product or the dehydrated addition product. What factor favors the formation of the dehydration? Okay. So conveniently in their image, they're giving me what the addition product is and what the dehydration product is. So the first thing that I went through and did was to compare the difference between those. The big difference to me was that I had an alkene in the dehydration, which meant I got rid of that hydrogen, looking at the wrong screen, that hydrogen, and I got rid of that hydrogen. Okay, so we're trying to identify the big changes. Once we've got the big changes, we can then start to make kind of conclusions about what happened. Okay? So what favors getting the dehydration product? Okay? So what has to happen is I will have to break a hydrogen off, and I need that OH to act as a leaving group. Okay? So excess aldehyde. That's looking at adding a bunch of this. Okay? It could have an effect, but that doesn't directly affect the things that I've already highlighted. Okay? Excess base. Okay. Having a lot of base could help remove this hydrogen. So that could help. Okay. But having a bunch of extra base could also remove that hydrogen, so that could hurt. Okay. So excess aldehyde is questionable. Excess base is good and bad. So plus and minus. No alpha hydrogens. Okay. Well, the alpha position is referring to our carbonyl as a 0 position. The next carbon would be our alpha. If there's no alpha hydrogens, well, then I can't do the elimination. So that answer is absolutely wrong. Makes no sense. The last one, stabilization by conjugation. Okay. Well, again, the question is now saying, why is the dehydration favored? So if I compare the dehydration to the addition, is there a conjugation stabilization in the dehydration? Well, conjugation just means that I have a pi bond offset from another pi bond. by a single sigma. This pi bond and this pi bond are in resonance. That's conjugation. Conjugation gives us resonance. That is stabilization. That absolutely favors the dehydration. I have a more stable structure. I don't even have to know that that is the reason we do the conjugation or the dehydration from the aldol. I just have to be able to work through the answer choices given to me. Does that make sense? Okay. So I do expect you to have content through this semester, but a lot of it I do expect you to be able to interpret based off the information we've talked, to look at things and critically evaluate. Does that claim make sense? That one does. Does that work for that explanation?
Yeah.
Are there other ones? How did you guys do? Did anybody get them all right? 6 of 7? 5 of 7? You're counting? 4 of 7? 1 of 7? Oh, that wasn't, oh, hold on, wait a second. There's just one.
Well, I got 1.5.
1.5. Oh, I'll accept that. Okay. And we do this to show practice behind it, but also kind of the speed that you should be picking up. Okay. And I still notice that people are not writing on their exams. Write down information. When it comes to the final, one of the things that becomes more challenging is you're not allowed to write in the exam booklet. This is why I have tracing paper and blank scratch paper that you can write information down on. Okay. I would make the argument that what you should do is take just the blank paper and just quickly scan through the questions of the entire exam and be like 1, acid base, 2, name, 3, I have no idea, 4. And it should be like a fast, this isn't a long thought process behind it. It's reading, what is that question asking? What's that main topic? Write it down. Because then you finish that, you've now categorized things. If you've left it blank, that's already a signal that you're probably not going to answer that question right. Don't answer it. Okay, skip that one. Move to one of the questions that you at least recognize the content for. Does that make sense? Okay. This is not a 70 question exam. This is an exam with 70 questions that you ideally get 40, 45 right. Okay? So it's really a 40 to 45 question exam. Okay? The extra 25 is so that you can show off. Okay? So do not attempt to answer every question. That is a bad idea. Okay? To rephrase that, do not attempt to answer every question, but answer every question. Okay? That just means guessing. Guessing is fine, just do it. Okay? So, you want more on enolates or you want a different section? Different section? What drew you to 6?
Have any reagents or anything dealing with it?
Okay.
Like choosing them?
Okay. So, what did you see within question 6 to help you answer it? Okay, so that could be a problem. It's not NO2 minus. It's NO2. No.
Oh, see, I can't.
It's okay, I know. It's NO2 plus. Okay, so that might change your answer. We'll see what happens. Okay. And then we're asking the positions of the ring that would react with that. So that means the ring is acting as what? It's a negative charge. So which of those positions is more likely to have negative charge?
Probably the farther sides, like C and D.
Why C and D?
Because they're farther away from the carbonyl I was looking
So what you're saying is that that carbonyl is a partial positive because of the electron withdrawing of that oxygen. That's good. That means this ring is deactivated. The next ring would be less deactivated. Okay, I'll accept that. Okay, anybody want to add to that?
I would say the methyl is
The methyl is
it activated?
an activator. Okay, so the activator on that methyl is likely going to trump. Okay, so we're looking at the methyl group directing versus the carbonyl deactivating. So between C and D, what's that? C is at the meta position, and our activators direct the para-ortho. So if C is at the meta, what does that mean? The answer is D. Does that make sense? So each of those pieces kind of stack through it, and we have to be careful in how we approach those. We do have to make sure we read it carefully, okay? Which I will go ahead and volunteer this on this one, and then we'll push down to Sam. Question 3, I looked at this and said, oh, this is Friedel-Crafts alkylation. I just attached the carbon to the structure. So that's 1, 2, 3, 4 carbons. 1, 2, 3, 4, answer A. Sam, which question would you like to take a look at?
I'm going to start with 4.
Okay, you started with 4. Did you want to challenge what I just wrote up there?
Oh, number 3.
Oh, you said 4. Never mind. You started with 4. I lied. Go ahead. Tell me about 4. Tell me about 4. Tell me about 4.
I did the same exact idea as you. Yeah. But then.
Tell me about 4. Because that's what you said, right? You said 4?
Yeah, I did say
4. Okay. Tell me about 4. What do you see in 4?
Well, I saw the benzene ring with the activating substituent, the methyl group, which, like on 6.
Green is a horrible color.
Maybe think of the para-ortho.
Right. So it did go to the para position.
So we just added a bromine. So
What
it
charge would that bromine need to be?
would need to be a positive.
So which of those give me a positive bromine?
Maybe a.
Okay. B and C both give you a positive bromine. UV light is a tip off that you're doing a radical, so that's not a positive bromine anymore, that's a bromine radical, and God knows we don't want to deal with that. D you should eliminate immediately because it gives you a negative bromine. Okay. B, Br2 and CCl4. Okay, that is carbon tetrachloride. Why did it take me so long to come up with that? CCl4 is just a solvent. Okay. So why would A be a better answer than B? The solvent isn't going to make that positive bromine any more positive, right? So they're both going to give you positive bromines. Why is A a better answer than B? There's 2 answers. What do you got?
I just said that they can actually interact with each other. Okay.
Elaborate. What do you mean interact with each other?
One of the bromines on Br2 will attack the positive iron.
Yes. This is a Lewis acid catalyst. That Lewis acid catalyst makes the bromine a larger positive. Is a larger positive going to be necessary to get the aromatic ring to react? Yes, because aromatic rings don't want to react. A makes sense. So that would be the explanation of it. The other part is you memorize that when you do EAS, Br2 and FeBr3. Either's fine, you got there. Okay, so cool, I agree. Wyatt, what do you want to do? So officially we've got 3, 5, 7, and 8. 8. Okay. So what did you see when you looked at that question? So where I would go with that is that you've internalized something here. You've internalized intermediate. We talked about this a bunch. So that's good. You internalize it. Ideally write it down. Intermediate in the EAS reaction. Well, the aromatic ring acts as a nucleophile, meaning your intermediate is going to be an aromatic ring with a positive charge. So you have to be looking for the structure with a positive charge. B doesn't make sense because it has a negative. Okay?
The next thing I looked at was, since they're A, C, D are all just resonance of one another, the electrons are there.
Yep.
Look at A as a main positions, can we deactivate or do that? And since it says
If they're all resonant structures of each other, we can't do anything with deactivator.
okay.
What's the question asked? Why halogens in an intermediate? Right, so in the intermediate we're generating a charged structure. I want to see how the halogen affects the structure. Does A show the halogen affecting the reactive part of that structure? No, why not? They're too far away from each other. Right? C. I put them right next to each other, so that seems reasonable. D. What happened in D? It's on the bromine. How did it get there? The bromine literally added electrons to the positive charge. Which of those structures, C or D, shows how the halogen affected the intermediate? Only D shows the direct cause of that donation. C sets you up and gets you right there, but doesn't actually show how the halogen contributed. Make sense? Okay. Lydia? Okay. So 5 is one I would almost undoubtedly, and as I read through it, I immediately skipped over it. Okay. The reason why I skipped over 5, an awful lot of words, meaning I needed to know nomenclature. As we all know, I'm horrible at nomenclature, but eventually we got to come back to it. Propyl 1, 2, 3, benzene. Okay, so we're looking at a propylbenzene. So that is our first step. I apologize that I just took that first step away from you, Lydia. Your turn.
I eliminated D right off the bat, and
It's an interesting idea. The double bond in the part 2, we haven't seen anything like that, particularly with the Lewis acid catalyst. The alkene we have done. Okay, so let's take a look closer at D. CH3, CH2, or CH within the Lewis acid. Okay, which of those carbons would be the most positive? Red, blue, or purple? If we look at the most reactive thing, it's the pi bond. If we take electrons in that pi bond and look at resonance structures, it makes more sense to put the negative charge on the purple carbon, leaving the carbocation on the blue carbon being the most substituted. So that means even if I somehow D, those reagents somehow worked, the positive charge would be on the middle carbon, not at the end. To get propylbenzene, it has to be at the end. So D doesn't make sense for that reason. Okay.
I also eliminated C because it looks like a ring almost, and that makes a negative carbon,
Good.
which I didn't really see it attacking it.
Okay. That Grignard makes a negative carbon. Well, what does the ring have to act as? A negative charge. It has to be a nucleophile. Okay? It could potentially react as an electrophile if it satisfied all these other secondary conditions. Okay? That's pretty selective. That's not the case here. Okay? So C isn't a good choice.
And then I was down to those two, and I kind of chose B because it looks like 3, and it's very confident. And I
So
chose 3.
1, 2, 3 carbons, but 1, 2, 3 carbons, right?
Yeah.
Okay. So does this question look familiar to anybody else? What's that?
It's kind of like 3, which is wrong.
It's kind of like question 3, right? You just took a carbon chain with chloride at the end and aluminum chloride and you just ran the reaction. Okay? Why would you ask the same question? That doesn't make any sense. What's going on? Did I perhaps miss something? What did I miss? Because the top one's got more space, let's look at the top one. The whole point is the chloride leaves and I'd be left with a carbocation. What kind of carbocation would that be? Oh! We'll just ignore that. That would be a primary carbocation. What would primary carbocations do? Rearrange to put the carbocation in the middle of the structure. Which would then mean A was a horrible answer choice. And B, assuming, yeah, B then becomes the correct choice. Okay. Can I use that information in 5? Well, in 5, what am I trying to do? I'm just trying to get the straight chain. Well, if I just added in 3 a straight chain and it did a rearrangement, is that going to work in 5? No. So B must be wrong. The answer choice has to be A. Okay. I don't even have to like what A looks like, but everything else is wrong. Why is A the correct answer? We're going to do a Friedel-Crafts acylation. We'll get the carbon chain, but we'll have the carbonyl there. What is step 2? Step 2 is a reduction that gets rid of the carbonyl. Okay? So we may not remember the reagent. We might remember the reagent. It all depends on kind of the different circumstances. So we have to play with what we've got. Okay? And realize they will ask repetitive questions. Okay? It does happen. So don't just assume because you've answered a question that you can't go back and review it. Okay? But when you go back to review, which I talked about with Jenna and Elisa in just a few seconds ago, that when you go back to review, it's not well, I think it could be this, so I'm going to change my answer. No, it's this is the reason why my first answer is wrong. Now I can change my answer. It's not, well, I don't really know, so I'm going to change it. Don't change it. Okay? And it's not a huge favoring, but studies have shown that your gut instinct is right. Okay? It's when you go back and second guess yourself that you pretend to put the wrong answer. Okay? So you are fine to change an answer. That is okay. That's not second guessing. That's coming back and saying, no, shit, I was wrong. Okay? I drove the car into the tree. That was a wrong decision. I need to not do that again. That doesn't mean like, well, I don't know. No, it was wrong. Don't do that. Okay, you have direct evidence to support it. It's not like, well, I parked in slot A versus slot B. I don't really know which slot was better. There's no reason to change. Don't change. Okay. Does that make sense? Okay. And yes, that is frustrating because you will be sitting there and second guessing yourself. Until you are positive of your challenge, don't change it. Okay. That's my recommendation, at least. Okay?
Another question.
Yeah.
So just on number 5, is that acylation, is having that carbonyl not allow the rearrangement to happen?
True. The rearrangement doesn't happen with the Friedel-Crafts acylation like it does with the alkylation. So if we draw, let's just draw out the propyl above. Okay. So that would be answer B from down in question 5. I'm just going to do them both up there. The alkyl carbocation will rearrange because that's a primary carbocation. The acyl carbocation doesn't rearrange, and that's because there's resonance to stabilize it. It's that resonance stabilization that keeps it localized, okay? Which is a really weird statement to make, but I made it and I accept stand by. Okay. Localizes the chemistry. It's the acylium ion. Okay. So across to the other side, with what? We got one question left? 7. Duke, you want to give it a swing? Yeah. What do you see within it?
What do I see?
Yeah. So when you go through...
Between B and, B and D.
Okay. So you got stuck between B and D. So what's the work that you've got to kind of set this up? And this is admittedly a hard one.
So the OH comes in and attack the carbon that's attached to the Cl.
Right, so it would attack there, but then it would exceed the octet, so what has to happen?
The Cl leaves.
Okay. We could have the Cl leave. Okay. That would be an SN2 type mechanism. If we did that as an SN2, the OH had to attack from the backside of that carbon-chlorine bond. The backside of that carbon-chlorine bond is the ring. Okay. Can it do that attack? Okay. And other people can chime in here. You don't have to leave Duke hanging. No. The aromatic ring cannot do SN2 reactions. That doesn't work. Okay. So you're right that those two things need to happen, but the question now becomes the order in which it happens. Okay. So they can't happen at the same time. Could the chlorine leave first? Well, then you'd have a carbocation. Are you allowed to have a carbocation on a ring? No. So how does this reaction occur? And this is entirely my fault. We did not talk about the detail of this mechanism. Any ideas? If you've read about it, don't speak up. So we're still kind of stuck in this boat. The OH has to attack, the chlorine has to leave. The chlorine can't leave first. The OH can't attack at the same time the chlorine leaves. Okay? So we know those two things to be true based off of first semester substitution chemistry. So let's see what we can do with that and see if that eliminates any answers. It takes place in one step with no ionic intermediates. So one step means they're both happening at the same time. Well, we just said that can't happen, so A can't be right. It takes place in 2 steps, elimination, then addition. So what does that mean? But it says elimination. Elimination would mean we'd make a pi bond first and then do an addition to the pi bond. Okay? So that changes everything about the arrows up there, because the arrows are just looking at the substitution. Okay? So if we tried to do an elimination first, so the chlorine has to leave, and then our OH would have to come in and remove a hydrogen. Right? Okay. We've got an unfortunate location for the pi bonds of our aromatic structure. But this would be saying we'd go through and form the benzyne intermediate. Does everybody see that that would be the natural result of that elimination? Okay. You don't have to. what we need to check and verify. Everybody okay with that? Okay. If we did that, then our OH would then have to come in and attack. Where would it attack? It's going to have to attack the reactive position, that pi bond. Well, which position? Is there any difference between those? Not really, which means two products. How many products are shown? One. Okay, that's hard because that requires a lot of kind of thought process through, but that would suggest B is wrong, and we'll put a question mark on that because that took a little bit of work. C, it takes place in two steps: addition, then elimination. Okay, well, geez, yet another mechanism. So addition, we're saying the OH comes in and attacks, but then we'd have to break a pi bond. Okay, so this pi bond would have to break somewhere. Okay, so I could shift that over to here. Would I be allowed to do that shift? I meant to do that in a different color. I don't know, what happens? So I should have going directly to forming a pi bond, but we could just say, let's put it as a negative charge. Either's perfectly valid. What can you tell me about the nitro?
It's possible.
Is this negatively charged species resonance stabilized? Yeah. So is that addition step something that could theoretically happen? That may be ugly and awful, and God, Mike didn't talk about that. But I haven't drawn anything like horrible. I may not be happy about it, but I haven't drawn anything horrible that just looks weird. So I'll put a big old question mark next to that, but I can't really eliminate that. The next part would be an elimination. Well, that would make sense because I would need to reform that pi bond and kick out the leaving group. Okay. D, it takes place in 3 steps and involves a carbocation intermediate. Okay, well, can I form a carbocation? No. So D has to be wrong. So I'm now stuck between B and C, where B, both of them are questions, but B has me leaning towards it being wrong. That means I should stick to C. Okay? Don't have to be happy about it, but we're just kind of looking at what are the pieces. Okay? And notice we're using the text to draw results. We aren't just saying, well, that doesn't make sense, I can't do that. I'm drawing it to be like, yeah, I didn't like that. That looks really weird to me, but I can draw arrows that make sense. That's cool. Do that. Right? Particularly with something where you're like, I don't even know this. That is my fault. I should have drawn out the mechanism. I apologize. The answer is indeed C. Right? There are 2 mechanistic steps that we can do on aromatic rings to have them act as electrophiles. One is the benzyne intermediate. That's the elimination and then the addition. That generates 2 products. That is the benzyne. We did talk about that, didn't show it a lot, but we at least addressed it. The other one is the reverse, the addition, then the elimination. Right. That is what is known as our nucleophilic aromatic substitution, or our SNAR. It's really doing an addition followed by an elimination. Okay. So B and C are the 2 weird mechanisms for aromatic rings. B is weird because that gets us the benzyne. C is weird because the ring is acting as kind of an electrophile. Does that make sense? Okay. If you look at a question and you're like, nope, that's fine. Accept it, just move on. Don't burn time on it. Okay, make sense? Questions about any of that? What do you think? More confident or less confident?